Redox Processes 1. Oxidation and reduction. Essential idea. Redox or reduction oxidation reactions play a key role in many chemical and biochemical processes. Nature of science. How evidence is used changes in the definition of oxidation and reduction from one involving specific elements, oxygen and hydrogen, to one involving electron transfer, to one involving oxidation numbers, is a good example of the way scientists broaden similarities to general principles. Theory of knowledge. Chemistry has developed a systematic language that has resulted in older names becoming obsolete. What has been lost and gained in this process? There's many examples of redox reactions, and you can just see a few here. For example, batteries. There's redox reactions going on inside of chemical batteries. We have redox reactions taking place rusting, when an apple browns, gold plating, fireworks, etc. So what are oxidation and reduction reactions? Well, these are reactions that involve a transfer of electrons from one reactant to another. Redox reactions always have two half reactions. The oxidation reactions, which is the loss of electrons, and the reduction reactions, with the gain of electrons. And you can see the oxidation reactions are obviously going to give electrons to the reduction reactions. This makes sense since oxidation reactions are losing electrons. These half reactions are always paired together or coupled. Electrons move from the oxidation half reaction to the reduction half reaction. What are oxidation and reduction reactions? Well, we've got some nice little ways of remembering these. LEO is loss of electrons is oxidation. Oil rig. Oxidation is loss, reduction is gain, and I want you to go and try and find out what Elmo is yourself. Electron gain and loss in redox reactions. Example 1. Synthesis reactions. We've got magnesium reacting with oxygen to give magnesium oxide. This is the overall redox reaction. So what we can do is we can separate this ionic compound into its two ions. So we've got two magnesium ions, we've got two oxygen ions. And then to do the two half reactions, we can look what's happening to the magnesium. You can see magnesium, the metal is giving the ion, and the oxygen is giving the ion. So you've got a molecule of oxygen giving two oxygen ions. Here you can see magnesium is giving up electrons and oxygen is reacting with electrons, or it's taking in electrons. So electrons are lost. We know now that loss of electrons is oxidation, and electrons gained is reduction. Example 2, synthesis reaction. Press pause, see if you can complete this. Okay. Zinc metal reacts with iodine to produce zinc iodide. Write the overall equation and the ionic equation. Well, we've got zinc and iodine to give us zinc iodide. So let's split that ion up into the zinc ion and the iodide ions. Then we're going to split it into two. So we obviously have the zinc metal giving us the zinc ion and two electrons. This has given up two electrons to form the positive ion. And iodine is reacting with two electrons to give us the anion. So this is losing electrons, therefore oxidation. This is gaining electrons, therefore reduction. Next, example 3. Press pause, see if you can do it. Okay. Sodium chloride splits into sodium metal and chlorine gas during electrolysis. Write the overall equation and the ionic equation. Sodium chloride gives you sodium and chlorine. Let's split this into its two ions. And now we're going to split the equation into two. So let's have a look what happens with sodium first. Sodium, the ion is reacting with two electrons to give us sodium metal. And the chlorine ions are giving us the molecule and giving up 2 electrons. So this is gaining electrons, therefore it's reduction. And this is losing electrons, therefore it's oxidation. Okay, pause again, have a go. Well, zinc metal with the HCl to produce hydrogen gas and a new compound. Zinc metal with oh, this is incorrect. Zinc metal reacts with HCl to produce hydrogen gas and a new compound. Write the overall equation and the net ionic equation. So we've got zinc and hydrochloric acid giving us zinc chloride and hydrogen. We can split the zinc chloride up and we can split the HCl up. So let's have a look at this. We want to split into 2 half reactions. First thing we can do straight away is, you can see we've got some observer ions here. These are the same on either side of the arrow. Look, the zinc's changed. It's gone from a metal to an ion. You can see the hydrogens changed, ion to molecule, but the chloride ions are identical. They're observer ions, so we just don't need to worry about them. You can put a nice little red line through them. So let's look at the zinc. We can see zinc is giving up electrons to form the ion, and you can see that the hydrogen ions are taking some electrons in to form a stable molecule. So zinc is losing electrons, so it's reduction. The hydrogen ions are gaining electrons, and so it is oxidation. Some older descriptions for redox reactions. The transfer of electrons is not always evident in reactions involving covalent compounds and organic compounds. For example, you've got a sugar with oxygen giving us carbon dioxide and water. It's glucose. This is just cellular respiration. It happens in every cell in your body, and the glucose is being oxidized. The 2 half reactions are the glucose going to the carbon dioxide and oxygen giving water. Now, when hydrogen is lost or oxygen is gained, that is also oxidation. So instead of thinking about movement of electrons, you can think about hydrogen and oxygen. This is the way people used to think of it. So when hydrogen is lost, and you can see that glucose is giving up its hydrogen from carbon dioxide, therefore it's oxidation. Okay? So conversely, when hydrogen is gained, it's a reduction. And you can see we've got oxygen here, it's gaining a hydrogen, therefore it's reduction. Okay, another way of thinking about redox. Let's consider this reaction. We've got carbon dioxide and water giving us glucose and oxygen. Yes, you've guessed it, it is just the exact opposite of what we saw, so it must be our good friend photosynthesis. And we're looking at the reduction of carbon, 2 half reactions. We've got carbon dioxide giving us sugar, or this glucose here. We've got water giving us oxygen. Then you can see here, we're definitely gaining a hydrogen, okay? Or you could think of it as losing oxygen. There's 12 oxygens there if you were to count them up, only 6 here. Therefore, this is a reduction. And you can see we're losing a hydrogen. Obviously, we've got some hydrogens there, and it's going straight to the oxygen. And so this is oxidation. Example 3. Consider this reaction. We've got ethanol reacting with X to give us ethanoic acid and Y. So, if you have a reaction where ethanol is going to ethanoic acid, I mean, you can see straight away the oxygens are being gained, right? One way of thinking about it, like we just did. This reaction here is used in breathalyzer reactions. So when you're driving along and you've had a drink and a policeman pulls you over, asks you to breathe in a funny gun, this is the reaction that that funny looking gun thing is checking for. The 2 half reactions, and you can see here straight away you've got this dichromate ion, which you'll get to know this very well. And you've got some protons giving us chromium 3 plus and water. Well, we've got ethanol going to ethanoic acid, and we've got X going to Y. Obviously, hydrogens are being lost. Just count them up and have a look. And oxygens are being gained. That's more straightforward to see. And so it's oxidation. This would be reduction, because it's the other half of the reaction. And if something's being oxidized, something else is being reduced. Oxidation states are a way to keep track of how many electrons an atom gains or loses in a redox reaction. Oxidation states have two parts. They've got a plus or a minus sign. The plus sign is when the electron moves away from an atom. Minus sign, electrons move towards the atom. They also have a number. So a plus or minus sign and a number. The number is the number of electrons they've moved. And it's important to remember this, and you're bound to get it wrong at some point, because at other times you write the sign and the number the other way around. But for oxidation states, you must always write oxidation state with the sign before the number. To help you remember this, there's this nice star, and always before is in capitals, ensuring that you will never forget this fact. We assign oxidation states to atoms of each element in a substance. You can see here a bunch of substances. We've got carbon dioxide, aluminium sulfide, potassium sulfate. We've got ethanol and oxygen. And here you've got all these oxidation states. Carbon in carbon dioxide is +4, oxygen is -2. If we look at the potassium sulfate, the potassium is +1, the sulfur is +6, the oxygen is -2, etc. But of course you are asking, how do you know these oxidation states? There must be some rules. I'm sure you're begging for some rules, and you're in luck, because there are some rules for you to learn and then commit to memory. Pure elements. Any pure element has an oxidation state of 0. So diatomic molecules, pure sulfur, pure carbon, silicon, any metal, etc. has an oxidation state of 0. Monatomic ions. Any element as a single ion. Well, the oxidation state is just the same as the charge. So if you've got Na plus, sodium plus ion, or the potassium plus ion, its oxidation state is +1. If you've got aluminium 3 plus, or iron 3 plus, oxidation state is +3. You get the idea. Bromine -1, oxidation state -1. Very straightforward, which is nice. Oops. 3. If hydrogen is in a compound, there's two rules. Hydrogen in the majority of compounds has an oxidation state of +1. Okay, so here in water, it has +1, so the overall would be +2, because there's two hydrogens. Here, each hydrogen has a +1, so overall for hydrogen, it's going to be +4, because there's 4 hydrogens, etc. But in metal hydrides, when hydrogen is bonded to a metal ion, then its oxidation state is -1, such as in sodium hydride, lithium hydride, etc. Oxygen in a compound. Oxygen in most compounds, -2. In water, -2. In the glucose that we just looked at, in carbonates, magnesium oxide, etc. But you can get the oxidation state -1. This will be in peroxides when you've got the two oxygens like this. In hydrogen peroxide, sodium peroxide, etc. Group 5. Group 1 and 2 metals in a compound. Any group 1 metal in a compound, oxidation state +1. Any group 2 metal in a compound, +2. So very straightforward. Okay, so sodium, potassium, lithium will always be +1. Calcium, magnesium, barium, all those group 2 metals, always +2. 6. Group 7, or 17 to be more precise, halogens in a binary compound. Any halogen in a binary compound has an oxidation of -1. So bromine, calcium, iodine, fluorine, etc. all have an oxidation state of -1. 7. Now this is the bit which is not tricky. If you remember the first 6 rules, it's straightforward. But you do have to know the first 6 rules to then make this bit easy. Okay? So any other element except those in the first 1 of 6 rules can have various oxidation states. It just depends. But if you have a molecule that doesn't have a charge, then the oxidation states of the two elements within there must equal 0. Or if you've got 1, 2, 3 different elements, and look here, you've got 3 of the oxygens as well, the overall charge of this must equal 0. Okay, so let's have a look at this. You've got sulfur and oxygen. We know oxygen in this situation from one of our rules is -2. We've got 3 of them, so 3 times -2 would be -6. X has to balance that -6 to give us an oxidation state of 0 overall. So, not an oxidation state, sorry, an overall charge of 0. And so X must be +6 if this is -6. C2H4. We've got, in this situation, we know hydrogen is +1. It's not a halide, so it must be +1. We've got 4 of them, so 4 + 1 gives us +4. We've got to balance that, okay? And we know carbon is going to have a charge of X, sorry, an oxidation state of X. We'll be careful saying charge. Oxidation state of X. There's 2 of them, so 2X needs to balance with 4. And we know that 2 times 2 would give us 4. And so this must be -2, because this is +4. Sodium, bromine, and oxygen. A bit more tricky because there's 3 of them. Sodium, it's in group 1, so we know it's +1 oxidation state. Oxygen, we know is -2. There's 3 of them, so 3 times -2. So we've got 3 times -2 is 6, and +1. Add them together. We get -5. That needs to be balanced to make 0. So -5 and +5. So X is +5. Chlorine and oxygen. Oxygen, -2. There's 2 of them. So 2 times -2 gives us -4. The overall charge must be 0. So X has got to balance -4. So it must be +4. C3H8. Not a halide. So H is plus. H8 multiplied by +1. It's going to be 8, obviously. We've got 3 carbons. So there's going to be 3 X's to balance it. And so to get 8, it's going to be, this is +8. Got 3 of these, so it's going to be -8 over 3. Again, the same thing, but this time the difference is we've got charges here. These are all ions, polyatomic ions. Okay. The only difference is from the last slide we did. In the last slide we did, this charge is really just 0, isn't it? And so instead of having 0 here, you just have what the charge is. So let's do it slowly. We've got oxygen, okay, and we've got 3 of them, each with the oxidation state of -2. 3 times -2, -6. We need to balance it with X to make -2. So we need -6 and +4 gives us -2. ClO4 minus, O4. We know oxygen is -2, we've got 4 of them, so we've got -8 here. Overall minus charge of -1. So to get an overall -1, if this is -8, this is going to have to be +7. Here we've got 2 chromiums, 7 oxygens, 7 minus 2, overall charge -2. This is going to be -14. We've got 2 of these, so -14, and you've got the -2 over here, remember, so X is going to be +6. NH4 plus, you've got hydrogen +1, you've got 4 of them, you've got a +1 over here, so this is going to be -3 to balance that +4. You've got +4, -3, overall will give you +1, and finally we've got PO4 minus, we've got oxygen, -2 oxidation state. There's 4 of them, and we're trying to balance it to -3. So we've got -8 here. If we've got -8, we're going to need +5 on this X to give us -3. Okay, press pause and have a go at all these. go. Give yourself a big fat tick if you've got them all right. IUPAC names for polyatomic ions. You name the stem of the first element plus 8. Okay? And the oxidation number of the first element. So, you've got here sulfur and oxygen. We know oxygen is 2 minus oxidation state. There's 8 of them, so it would be 8 minus. You see the overall charge is 2 minus. So sulfur must be plus 6. Indeed it is. It's plus 6. Okay. So to name it, sulfur, because we've got sulfur. Okay. We know it's 8 ion because they're all oxygen. 8. And then you want to have 6, and you've got no Roman numerals, and Vi is 6. Next one, you've got sulfide ion. You've got 3 minus 2s for the oxygen, so minus 6. Overall 2 minus, so sulfur is plus 4. So it's sulf. Okay, the old system would be 8 because you've lost 1. New system, you write 8, and you'd write the Roman numerals of the oxidation state of the sulfur. Bromate, same thing as up here. You've got, but it's only minus here, so you've got 6 minus altogether. Got to balance it because you've got a minus here, so it's going to be 5. Bro, 8. V. I think you get the idea. Okay, have a go at these. Press pause. Excellent. Well done. Hopefully you got them all correct. If not, go back at the ones you got incorrect and just see if you can find where you went wrong. Okay, using oxidation states to identify oxidation and reduction reactions. Reduction reactions is gain of electrons. Decrease in, you get a decrease in oxidation state. You see here magnesium with an oxidation state of 2. Getting 2 electrons to get an oxidation state of 0. 2 going to 0. Here, oxidation state of 3 going to an oxidation state of 2. The oxidation state is decreasing. You're gaining electrons, decreasing in oxidation state. Tie these two together in your head so you don't need to think about it. Oxidation reactions, loss of electrons. You get an increase in oxidation state. You can see here we've got 2 minus on the sulfur going to 0. The oxidation state is increasing. You've got minus 2 to 0. It has got larger. Here, 0 to plus 2. Again, obviously oxidation, 0 to plus 2 is increasing, and we're losing electrons. Deduce and explain the substances reduced and oxidized in this top one. Well, first thing you do is assign oxidation numbers. So, we know how to do this. We know oxygen is minus 2, we know sulfur is, and we calculate the sulfur is plus 4 from the minus 2. Oxygen, it's a molecule, so it's going to be 0. It's an element state. And then we've got minus 2 oxygens, 3 of them. We know this from one of the rules. So we can calculate the sulfur is plus 6. So sulfur dioxide is oxidized because the oxidation number of sulfur increases from plus 4 to plus 6. The oxygen is reduced because the oxidation number of oxygen decreases from 0 to minus 2. Show using oxidation states that the conversion of ethanol into ethanal and then ethanoic acid are oxidation reactions. Well, we've got ethanol plus X giving us ethanal plus Y plus ethanoic acid plus Z. And you're going to learn a lot more about this particular series of reactions later on when we do acids and bases. So let's write these things out and and assign oxidation states. So we'll rewrite them out as simply as we can. You can see we've applied the oxidation states to each element, and then you can just look at each element separately and see what's going on. You can see that oxidation number for carbon increases from -2 to -1 to 0. Therefore, we are getting oxidation. Some definitions, which of course, whenever it says define, it's good for you to whip out a flashcard and get this one stuck in that memory. Okay, this is definitely a flashcard moment. An oxidizing agent is the reactant that accepts electrons, the reactant that causes another substance to be oxidized, the reactant that is reduced. The oxidation number decreases. A reducing agent is the reactant that supplies electrons, the reactant that causes another substance to be reduced, the reactant that is oxidized. The oxidation number increases. Here we've got magnesium and oxygen giving us magnesium oxide. Obviously 0 and 0 to begin with, both in the elemental states. And then we get the ion. Magnesium is the cation, oxygen is the anion. Magnesium has increased in oxidation. It has lost electrons. Okay, oxidation number is increased. Therefore, magnesium is oxidized. Oxygen, the oxidation number is decreased. Therefore, oxygen is reduced. So, if magnesium is oxidized, it must be the reducing agent. Okay, so whatever is oxidized is the reducing agent. So obviously, oxygen is being reduced, so it must be the oxidizing agent. Some common oxidizing agents, what's it say here? Show that the reactant is in blue acts as an oxidizing agent. So let's have a look at this. So oxygen here reacting with sulfur dioxide, iron, hydrogen. What else we've got? We've got ethanol reacting with the dichromate ion to give us ethanoic acid. And it's talking about fluorine and chlorine. And the halogens have high electronegativity values. Therefore, they easily remove electrons from other substances. Let's look at oxygen first. You can see that the oxygen here has an oxidation state of 0, and then sulfur trioxide in this it has the oxygen here, sorry, not the sulfur. The oxygen in sulfur dioxide has an oxidation state of -2. Here, oxygen's gone from 0 to -2, and here 0 to -1. So the oxidation number of oxygen decreases from 0 to -2, or in this case, from 0 to -1. Therefore, oxygen is reduced. Therefore, if it's being reduced, it is this molecule here is the oxidizing agent. Okay. The dichromate ion, chromium here, it has an oxidation state of 6, and it's going to an oxidation state of +3. The oxidation number of chromium decreases from +6 to +3. Therefore, chromium is reduced. Therefore, this thing here is the oxidation, the oxidizing agent. The dichromate ion is the oxidizing agent. Some common reducing agents show that the reactant in red acts as a reducing agent. Well, we've got hydrogen reacting with sulfur, you've got carbon as a reducing agent with water, and you've got some metals. You've got zinc as an example, reacting with copper chloride. So here, hydrogen within the hydrogen molecule has an oxidation state of 0, but hydrogen within this molecule has an oxidation of +1. So the oxidation number of hydrogen increases from 0 to +1. Therefore, the hydrogen is oxidized, and therefore the thing it was in, the hydrogen molecule, is the reducing agent. Here, carbon's gone from 0 to +2. The oxidation number of carbon increases from 0 to +2. Therefore, the carbon is being oxidized. Therefore, the carbon here is the reducing agent. And the metals, we've got zinc going from 0 to +2. So the zinc is obviously being oxidized. The oxidation number is increasing. Therefore, zinc is the reducing agent. Identify the oxidizing and reducing agents in these reactions, giving a reason. Press pause, have a go. So let's do the top one first. Identifying the oxidizing and reducing agents in these reactions. Let's look at the reason, shall we? Well, we've got potassium, 0, oxidation number of potassium increases to +1, therefore it's oxidized. Therefore, if the potassium is being oxidized, then this must be the reducing agent. The oxidation number of bromine reduces, it decreases from 0 to -1, therefore bromine is being reduced, therefore the oxidizing agent must be the bromine. Here we've got silver being oxidized, and silver, the oxidation number increases from 0 to +1, therefore silver is being oxidized. If silver is being oxidized, then this is the reducing agent. You've got H2S, we've got the oxidation number of hydrogen is decreasing from +1 to 0, therefore the hydrogen in H2S is reduced. Therefore this must be the oxidizing agent. Let's have a look. We've got nitrogen here, oxidation state of the nitrogen atoms, 0 in this, and they are decreasing or reducing to -3 in ammonia, and therefore if it's being reduced, this must be the oxidizing agent. And the hydrogen here, 0 to +1, oxidation number of hydrogen is increasing, and therefore the hydrogen is oxidized, and so forth. This must be the reducing agent. Here we have carbon monoxide. The carbon has an oxidation state of +2. It's increasing to +4, so the carbon is being oxidized, therefore this must be the reducing agent. Nitrogen monoxide got +2 going to 0, so the nitrogen has changed from +2 to 0, so it's being reduced. Oxidation number is decreasing, therefore if it's being reduced, this must be the oxidizing agent. Okay, and finally I would like you to go back through that quick as you can and complete this sweet little table as a summary. And that's the end of this presentation. Splendid.